I'm Toon Huysmans. I'm an assistant professor here at the Department of Human-Centered Design in the TU Delft. I have a background in computer science, PhD in statistical shape modeling, both from the University of Antwerp. And currently I am at the TU Delft, focusing on physical ergonomics and digital human modeling. So a lot of 3D scanning. And I'm responsible for making the DINED platform, which probably some of you know, the anthropometry platform, to make it future-proof by adding state-of-the-art tools and 3D and 4D scanning data to it. And yeah, that's what my talk will be, or the topic of my talk will be today. So the title is DINED Mannequin, an open 3D anthropometry platform. Let me share my slides. Okay. So yeah, many of you might know DINED. It's a platform for anthropometry, and it is mainly focused on traditional anthropometry, so summarizing one-dimensional measurements and looking at correlations between measurements. But it is not always satisfying or sufficient when you're designing specific products. So here you can see an example of why that is. We have three different people here, different body shapes, and I indicated the waist circumference with these three subjects. And you can see that there is a range going from 60 centimeters to 1 meter and 30 centimeters. But that number that is typically reported with traditional anthropometry, it is not capturing all the information that's there. Looking on the right, you can see a number of corresponding cross sections of this waist circumference. And then you can see that the shape is completely changing when you go from the lower weight to the higher weight person. So the conclusion here is that traditional anthropometry does not always tell the full story. So then we look at new techniques, techniques that use 3D scanning and 3D scanning data. And here you can see what the advantages of 3D anthropometry. So on the left side, we have the EN960 mannequin, which is used in testing and design of head protection, like cycling helmets. You can see that it's not really a very realistic head shape. If you then compare it with a result from 3D anthropometry in the middle, then you can see that this is a much more plausible average head shape, and it also shows the facial geometry and the ears. Another example is on the right, where you on the one hand have the white mannequin, which is a full body representation, which is based, it's P50, so it's an average subject, and it is based on the one-dimensional data in the DINED database. But you can also immediately see that it's not very realistic if you look closely at the shape. On the far right, you then see what this mannequin would look like if you use 3D scanning data. So these kind of 3D anthropometric studies, they are especially useful for the design of wearable products that have to closely and snugly fit to the human body. So then we're working with 3D scans, but 3D scans can be very challenging. As you can see here, a number of people have been 3D scanned, but you can see there are various holes, there are some spikes, some parts are connected, and most importantly, the number of points is very different between the different subjects, and the points are also located at different positions on the surface. So this means that it's very difficult to work with this. If you want to calculate an average, ideally you want to average the point, for example, the tip of the nose with the tip of the nose of the other two subjects, but it's not possible here because there is no correspondence between the 3D scans. Now, we have developed here techniques to solve this problem. And this is, it's a bit technical, but it's called, it's a very important technique. It's called template fitting. And it's explained here in this slide. So what you see here in the middle is a template. It's a kind of a generic body shape. And it also has a nice mesh associated with it. So you can see these blue lines. And then we use this template and we deform it in each of the subjects in our database. And here I show this result for 2 subjects. Subject 1, you can see the 3D scan here, and then we take the template and deform it on top of this subject. You can see here that the subject and the template, they match really well. So it's the same shape. But on the far left, you can see that it has a completely different structure than before. So actually, this is the shape of subject 1, but it has the points of the template. And we can do the same thing for subject 2. We also deform the template into subject 2. Then we get the shape of subject 2, but again with the same mesh. And this, doing this for all subjects in the database allows us to do statistics with these 3D shapes. And it allows us to do something like the calculation of an average shape, which you see here, the P50. So this is an average subject based on 1,000 3D scanned Dutch males and females. But of course, the average does not tell the whole story. So you have an average, and usually you have a standard deviation. And the standard deviation, we can also do that for 3D scan databases, but then it's called a shape mode. And we typically have a number of shape modes. And the first shape mode that we can see, it captures the most prominent variation in the shape that we can see in the database. And usually this is body size. And in this case, it's also related to body gender or to gender, because males are typically larger than females on average. So if you go here from the P2.5 to the P50 to the P97.5, you can see a gradual change in size. You also have a number of other modes. For example, the second one illustrates body mass index. The third one is related to body posture. And the fourth one also relates to gender. So this is a very nice way to visualize and capture the variation of 3D shape, body shape present in a database, but it's not very intuitive to work with. To make it more intuitive, we relate these 3D body shapes with their subject measurements. So like with body length, body weight, head circumference, things like that. And then we can use these simple parameters to steer the shape of this 3D body. And we can steer this shape to explore what kind of body shapes are present in a population. And we developed an intuitive tool for that. And this is now part of the DINED website. So here you can see the DINED website, a screenshot of it. And we already had the tools like 1D database, ellipse, profiler, reach envelopes. And now we have the Mannequin tool. The Mannequin tool is for 3D antropometry, and it's basically about what I've been talking about in this presentation. I will quickly go through how it works. So typically we start by selecting a population. And we have the Caesar database here as the population. So these are Dutch full body scans. And then we think about the product that we want to design. In this case, we're looking at a wetsuit, for example, surfing wetsuit. And then critical body parameters are the length of the person, so body stature, and some measure of chest circumference or body mass. So we select these 2 critical measurements, and these will become the, let's say, the space in which we're going to explore the body variation of the Dutch males in this case. So then you create a number of personas. So these are individual body shapes, and you start filling in the values for stature and body mass. And then you immediately get the most plausible 3D body shape that is connected to those measurements. And you can also see here in the scatter plot the complete distribution of body scans. So these are about 1,000 body scans. Each point is one individual body scan. And it shows you where the personas are located in this, in this group. So this can be like the starting point for creating a sizing system for a wetsuit. And we are very happy with this new tool. We have full body data in this new tool, but also data on head, child head shapes from Lie Goto. Here we have an example usage of this new tool related to the new situation, the COVID-19 situation. We are all desperately in search of well-fitting masks, so personal protective equipment, but yeah, these masks that we order in China, they are not fitting very well. And so what you can do with DINED Mannequin is you can create a number of mannequins going from a typical small Dutch lady to a large Dutch female, a large Dutch male, and take these as the representatives for our Dutch population. And then in digital CAD software for textiles, you can reverse engineer these masks. On the bottom you can see a physical mask. You can cut it open and then flatten it out, and then you can make a digital replica of that. And then you can do digital fit testing. And then here you can see, for example, for the P95, that this is really way too small. And it might be better to come up with a sizing system instead of with a one size fits all. Yeah, you can also take this a bit further. This was static fit. You can also look at more dynamic situations. So here you can see two mannequins that were created with the DINED platform and then subsequently animated. So we use the database Mixamo, which is readily available online, and it contains a number of motions. But you can also do motion capturing and then apply this captured motion to different body shapes. It could be very interesting to do this in virtual reality and experience body height and shape from first-hand perspective. So that could be interesting for future development. So this dynamic body shape, we also use that for some examples or for some applications. Here you have, for example, the application of developing a wetsuit, which was done by Timon Staal. It's a graduation project here at the TU Delft. And he created a sizing system with our tool, creating a number of mannequins, going from extra small to extra large, and then designing on, for example, the average medium size, designing digitally a wetsuit. So this is done by drawing on the DINED mannequin a kind of pattern that is then unfolded to a two-dimensional pattern that can be cut from neoprene and then stitched together to get a physical prototype. But before you create a physical prototype, you can do some optimization iterations. For example, you can look at typical surfing motions and see digitally how the wetsuit would stretch. For example, here you can see the duck motion, which yeah, you can see around the buttocks that you get increased stretch of the neoprene material. And this is done all virtually, and in that way you can optimize the wetsuit for motion. And you can all do this before you produce the first real prototype. Of course, you still need to do tests with real people also. What do we envision to do in the future with our tool is to take this even a step further. So what you see in this slide is a computer animation, and it's not exactly how a human body deforms. At our faculty, we have 4D scanning equipment, where you can see here an example of, where we can really capture the actual soft tissue changes when you're moving your body. So we're also looking forward to incorporate this kind of data into DINED. And then last but not least, we introduced also an additional to DINED, the DINED Forum. And we envision this to be a knowledge base for anthropometry and digital human modeling. So I can all invite you to go over there and see what kind of questions there are posed. And if you have questions about anthropometry yourself, then you can post them there. And there's a lot of experts in the field that we hope to attract and help answer all your questions. So we're really excited about this tool also. So in conclusion, yeah, we introduced a new tool, the Mannequin tool and the Forum tool, and we think we are making DINED a future-proof and state-of-the-art platform for anthropometry and design. And in the future, we hope to convert this platform into a real hub for sharing of knowledge and data in this field. So yeah, thanks for your attention.